So far in this class, we've really considered the quantization of two types of different field theories. So we've considered free quantum field theories. That is to say, field theories with particles, but with no interactions. Okay, so there's really not very much interesting dynamics in these two different kinds of free field theories. And starting next week, we're really going to get into what I think the heart of this course is, which is the study of interactions in quantum field theories. But I thought it would be useful today just to step back a little bit and remind ourselves of where we've come and talk about a little bit where we're going. So the two theories that we've encountered so far in this course are the theories of a scalar field phi. Now, phi is a local degree of freedom, one operator per point in space-time. And the way that we quantize the field phi is we expand in a basis of plane waves. And the coefficients in this expansion are, well, if we thought of them as classical variables, they would just be the components of the field phi in momentum space rather than position space. But when we quantize the theory, we regard phi as an observable, which becomes an operator in the quantum theory. And so these a's and a daggers become operators, which we saw obey the usual algebra of a set of simple harmonic oscillators. And the frequency of each one of those oscillators depended on the momentum p. The basic observable in the theory is something that we call the propagator, which I'll usually denote d. So the observables will be expectation values of phi or products of phi. And the simplest expectation value that we could imagine computing is the two-point function, which you can think of as a quantity that describes the probability, or more specifically the amplitude, for a particle to be created at x, travel to point y, and then be destroyed again, or alternatively to be created at y and then propagate to point x. And this guy is something that we computed, and I'll just remind you of the form for this propagator. It's an integral d3p of a momentum space quantity, which was the phase factor e to the ip x minus y, divided by the energy, which is p squared plus m squared. It will be convenient for us to study not precisely this propagator, but instead what is known as the Feynman propagator, which we defined as the time-ordered product of phi x times phi y. This time-ordering symbol just says that you compute the expectation value of phi x, phi y, if x is after y, and phi y, phi x, if x is before y. And we found a very nice expression for this Feynman propagator. If we converted our expression for the propagator as an integral d3p into a form that is a little more consistent with the idea that we should write things in a relativistically invariant way, so we write it as an integral d4p. Using the fact that that 2EP you could think of as arising from a contour integral where you integrate over a contour in the p0 plane, and then which propagator you got depended on which contour you chose. And so the contour that gives you this Feynman propagator is the one that was defined by this I epsilon prescription here. Okay? And in this 4-vector in momentum space, the form of the propagator took a very simple form. It was just 1, or I, over p squared minus m squared. So this is the form of the propagator that we will use going forward in this class. And it's really the most convenient one because unlike this expression up here, this expression down here is manifestly invariant under Lorentz transformations. And if you wanted to, you could think about the propagator in momentum space rather than position space. And the propagator in momentum space is just, I guess we could call it d tilde, is just I over p squared minus m squared, plus that I epsilon. But for most purposes, that I epsilon will not be particularly important. It will just remind us at the end of the day which contour we need to use when we think about this as an integral over over p0. It tells us which poles to pick up from this denominator right here. So this was the basic theory of the spin 0 field, of the scalar field. We met one other free field. Well, I guess we also met the complex scalar field, but it proceeds almost identically, the quantization of the complex scalar field, to that of the real scalar field. Different, however, was the theory of a spin 1/2 particle, where the field is now a 4-component object, which again we quantize in terms of raising and lowering operators. So here we need to sum again over all of the plane wave solutions to the equations of motion, which in this case was the Dirac equation. So for a given momentum mode p, there were 2 solutions to the Dirac equation, which we labeled by a parameter s that runs from 1 up to 2. It labels the 2 different polarizations of a plane wave solution of the Dirac equation. So there were those 2 polarization vectors, us of p, where s runs from 1 up to 2. And there was a coefficient, AP, for each one of these 2 polarization vectors. And so here, I'm writing out explicitly this index A, which is a Dirac spinor index that runs from 1 up to 4. I'm doing that just to make everything very, very clear in the discussion that's going to follow. Although usually in this class, we're going to leave that spinor index implicit if we can, in order to not drown in a sea of indices. And then there was a corresponding raising operator, which multiplied a positive frequency plane wave solution with an e to the plus IPX rather than an e to the minus IPX. And the coefficients of that plane wave solution we called B dagger rather than A dagger, because psi is a complex field here rather than a real field. The complex conjugate field, or actually not just the complex conjugate field, but the barred field, which is related to the complex conjugate field by the multiplication with a gamma 0, we called psi bar, and that has a very similar expansion in terms of raising and lowering operators. So we just find it by taking the bar of the expression above. So we have a VA bar S e to the minus IPX and a corresponding APS dagger times e to the plus IPX. And just as with the quantization of the scalar field, these A's and B's are promoted to operators when we quantize the field. And the important distinction is that unlike with the scalar field, where we would describe a quantum theory of bosons, here, because we're describing a quantum theory of fermions, these obey the algebra of the fermionic simple harmonic oscillator. That is to say, they obey anti-commutation relations rather than commutation relations. So what that means is sort of interesting. It means that if you think of phi as a classical field, psi as a classical field, psi is some sort of, well, it's some sort of I won't say classical because classical is sort of a loaded word, but psi is an anti-commuting variable. So unlike the real scalar field, so for a scalar field, we think of the degree of freedom as one number per point in space-time. If you want to think of psi, you can't really think of psi as a set of 4 numbers per point in space-time. Or if you do, they're not the usual sorts of numbers that you're used to thinking about. They're not the numbers that you learn about in elementary school. They're the numbers that you learn about in graduate school, the numbers that don't commute with one another. So if you want to think of psi as a classical variable, if you think of phi as a classical variable, it's one number per point in space-time. Psi, you can think of as a classical variable, a set of 4 numbers per point in space-time. But because these raising and lowering operators obey anti-commutation relations, they're anti-commuting numbers. Okay? Sometimes they're known as Grassmann numbers. So a little later in this course, when we discuss the computation of path integrals involving fermions, we'll have to think a little bit more carefully about the mathematics of Grassmann numbers. But for the time being, you should just take this as a given that if you want to try and regard psi as a classical field, you'll need to remember that it obeys an anti-commutation relation. Just as when you multiply normal numbers, multiplication is commutative. 4 times 5 is 5 times 4. The rule for Grassmann numbers is that if you have 2 Grassmann numbers, say psi1 of x, or psi1 times psi2, that is equal to minus psi2 times psi1. If you want, you could think of them as little matrices that obey anti-commutation relations rather than commutation relations, or you could just think of this as a different kind of mathematical object from the sorts of numbers that you're familiar with. And in fact, it's a much simpler kind of mathematical object because, for example, psi1 squared is equal to 0 because it has to be equal to minus itself. So just as with the scalar field, the basic observable that we're interested in studying is the 2-point function. And this is not something that we had a time to discuss before I ended last week. So I'm just going to take a few minutes to give you a quick computation of the 2-point function. And before I do so, maybe I should pause and see if there are any questions. Maybe if none of you have a question for me, I have a question for you. Okay. So far in this lecture, I've said that the basic observable is the 2-point function because because the observables are the correlation functions. The basic objects of interest are correlation functions of observables. We could also imagine computing a 1-point function. Can anyone tell me what the 1-point function of a real scalar field is? The expectation value of phi in the vacuum state. Yes. Yes, that is true. But if you just imagine, let's stare at that expression for phi right here. Imagine computing its expectation value in the vacuum. Remember the defining property of the vacuum state is that it is annihilated by A. So A acting from the left on the vacuum state is 0, and A dagger acting to the right on the vacuum state to the right, the bra vacuum state, is also equal to 0. So if one calculates the expectation value of phi in the vacuum, it's equal to 0. We'll come back to this in a second, because not in a second, but later on in this course, because if we considered more complicated interacting field theories, or field theories where there was some potential v of phi that made phi want to be non-zero, that would be reflected by the fact that the expectation value of phi in the vacuum state would be non-zero. But for now, I just want to point out that the reason why I say the simplest observable in the theory is the two-point function is that the one that's even simpler, the one-point function, is equal to 0. So I just thought I would make that comment. Similarly, one could argue that the one-point function of this variable psi is equal to 0. Okay, so let's now think about how we would start computing this two-point function. So here I've written down the two-point function of two psi's. I've included those A and B spinor indices just to make everything totally clear. So I'm really computing a 4x4 matrix. Very quickly, it turns out that the answer for this 4x4 matrix is very, very simple. And if you think a little bit physically about what the spinor psi means, you should be able to guess what it is. Does anybody have a guess? So in order to understand physically what this psi is, well, you could just imagine taking two copies of psi, inserted, say, at a point x and a point y, and inserting them in the vacuum, taking the expectation value in the vacuum. And what would you get? You would get a product of a bunch of A plus B daggers times another A plus B dagger, all expectation value in the vacuum. But the A's and the B daggers, they all anti-commute with one another. So at the cost of introducing some minus signs, you could always move all of the A's to the right and the B's to the left, so that the A's would act on the vacuum. And then A annihilates the vacuum state. That's what the vacuum state does for a living. So that this would be equal to 0. Now, in fact, there's a very simple interpretation of this fact. If you remember that our theory of a Dirac spinor is a theory of a particle with charge. And the variable psi carries a charge. Because if you think about psi, if you think about the operator A, say, as the one that removes an electron, and the operator B is the one that creates a positron, both of those operations increase the total amount of charge by 1. And so in order to have a non-zero expectation value, you need to conserve charge. So for example, you could create an electron here at point x and then remove an electron here at point y. That's an operation that conserves charge. But you can't create an electron here and create another positron over here and keep the and preserve charge. Okay. Another way of saying that a little bit more formally is to remember that the symmetry that led to charge conservation was the phase rotation of psi, where you multiply psi by a phase. The action is invariant. The equations of motion are invariant, which means that the two-point functions will be invariant. And so if you think about it, what does that mean? That means that the two-point function psi A, psi B must be equal to itself times an overall phase. And the only number that's equal to itself times an overall phase is 0. So the fact that this two-point function is 0 is another consequence of charge conservation. So, whenever you're asked to compute anything in any physics class or life, the first thing that you should always do is think about the symmetries that the problem has. In the present case, we have a symmetry, this phase rotation symmetry that led to charge conservation. And symmetries will often, if not simplifying the problem completely, as they have here, where it's set it equal to 0, make the answer at least much, much simpler. Similarly, you could compute the two-point function of psi bar with psi bar, and you would also find that it's equal to 0. The only interesting, non-trivial observable is going to be the two-point function of psi with psi bar. I'm going to go ahead and compute that very quickly now. But before I do so, let me pause and see if there are any questions. No questions? Good. So let's just go ahead and compute that. So what have we got? Well, we just insert these two expressions here, the expansions for psi and psi bar, in a plane wave basis. So you have an integral d3p, an integral d3p prime over 2 pi to the 6th. That normalization factor, 2 times the square root of EP prime. And then you have a sum over S and S prime. And if you stare at the expressions for psi and psi bar here, so when you insert the psi on the left, the BP dagger is going to annihilate the vacuum acting from the left. And similarly, when you insert the psi bar on the right, this lowering operator B right here is going to annihilate the vacuum. So the only terms that you have left are the A times A daggers. So you have a U A S P times U bar S prime B P prime times E to the minus I P x minus y times the expectation value of A P S A P prime S prime dagger. Okay. Any questions on that? This is exactly the same sort of calculation that we did when we studied the real scalar field. The only difference being that now these A's obey anti-commutation relations, and we have these polarization vectors that are going along for the ride. I should call them polarization spinners, not polarization vectors. We'll get to polarization vectors in a little later in this class. Okay, so what is this expectation value? Well, remember that these A's obey anti-commutation relations, and in particular they anti-commute unless S is equal to S prime and P is equal to P prime, and they were defined with that normalization factor of 2 pi cubed there. So we can use the S prime delta function to turn this guy just into a sum over S, and the delta function for the P's will allow us to set P equals to P prime, and we can then use the identity that you either have proven or will prove by tomorrow at 3 p.m., which says that this is in fact a very simple function of P and the gamma matrices. So it's a 4 by 4 matrix, and so is the gamma matrix. It's a 4 by 4 matrix, and it's just given by P contracted with the gamma matrix. So if you put that all together, you arrive at an expression for the 2-point function, which is very similar to the expression for the real scalar field. You only have this numerator, gamma mu p mu plus m, which is a 4 by 4 matrix. But aside from that, this is almost the same expression that we have for the 2-point function of a scalar field. Now, typically when we write this expression, now that we've done this calculation, we can just remember in our heads that it's a 4 by 4 matrix, and so I won't actually write out those spinor indices, but it's important to remember that this is actually a 4 by 4 matrix expression. Any questions on that? So I'm going through this calculation a little bit quickly because it's very similar to the calculation that we already did for the real scalar field. Sometimes we will give a name to this, just as we called the propagator for a scalar field D. We could call this guy S. Again, it's a function only of x minus y. That's because of translation invariance. So the expectation value of psi x, psi y can only depend on the distance between x and y, or said a little bit more precisely, the invariant interval between x and y, which is the invariant quantity in special relativity. And just as we defined a time-ordered propagator for scalar fields, one can define what's known as the Feynman propagator or the time-ordered propagator for spinors, denoted SF. And this is defined to be either psi x times psi bar y if x happens after y, or psi bar y times psi x if x happens before y. The only distinction between the Feynman propagator for bosons as opposed to that for fermions is that we have to remember that we're treating fermions as anti-commuting variables rather than commuting variables. So when you change the order of psi and psi bar, we should put a minus sign here. At this point, this is a definition rather than anything else. Hopefully, it will become reasonably clear why this is the sensible definition to make. But at this point, you should think of this just as a definition for what I mean by the Feynman propagator or the time-ordered propagator of two spin 1/2 particles. Question?
Yeah, in your expression for the s x minus y.
Mm-hmm. Oh, sorry, there's an x minus y here.
Yeah.
Sorry about that. Yes. Sorry about that. Good. Any other questions? Okay. Yes.
X0 is equal to y0?
If x0 is equal to y, so remember, let's think about the case of a boson. Remember that if x0 is equal to y0, you have points that are space-like separated. So the commutator is 0, so that means it doesn't matter what order you put them in. Similarly, for fermions, the correct statement is not that the commutator vanishes outside the light cone, but that the anti-commutator vanishes outside the light cone. So in fact, these two expressions are equal if x0 is equal to y0. So I don't need to tell you which one is correct. Good question. Excellent question. Any other questions? Good. Okay. Again, just as with the real scalar field, it's going to be useful to write this in a form which is more manifestly Lorentz invariant. And the argument goes exactly as it did for the real scalar field. All that we do is we regard this denominator here as the contribution coming from a residue in a contour integral over the P0, the real P0 axis. And that allows us to write this as an integral d4p rather than an integral d3p. This numerator just goes along for the ride. And then the denominator is exactly the same denominator that we got when we studied the real scalar field, including this I epsilon that keeps track of which poles contribute when we do this contour integral. So that, for example, if x0 is bigger than y0, we close the P0 contour in the upper half of the complex P0 plane, and you get this guy. And if you have x0 less than p0, you close the contour on the other side, and you get this guy. And we have the same e to the minus I p x minus y. So this is the expression for the Feynman propagator of a spin 1/2 particle. Let me just make one comment about this. So one of the defining characteristic features of the propagator of a real scalar field is that it was a Green's function, in the sense that if you acted on it with the Klein-Gordon operator, you got a delta function. The same is true of this Feynman propagator here. So in particular, this operator is a Green's function, in the sense that if you took the Dirac operator, so here this is d by dx, so let me write a little x here to remind ourselves that that's d by dx mu, and you acted on this guy, you would get I times a delta function that sets x equals to y. Indeed, that's actually pretty easy to show. So to check that this is true, let's just imagine acting with this Dirac operator on the Feynman propagator. Well, every d by dx here just brings down a factor of p. So what you get is, from that d by dx mu gamma mu, is a factor of p mu gamma mu minus m, which gets multiplied by this factor right here, which is p mu gamma mu plus m. And if you stare at that for a second, what is that? That's p mu times gamma mu gamma nu. That's a symmetric combination of gamma mu nu, so it's equal to 1/2 the anti-commutator of gamma mu nu, otherwise known as g mu nu. So the term that's quadratic in p squared, in p mu, is just p squared. And then we have a minus m squared from the term that's quadratic in m. I guess if I wanted to make this very clear, I should probably relabel the dummy index here to call it nu. And so that p squared minus m squared just cancels the denominator here. And you get the integral d4p of e to the minus I p dot x minus y, which is otherwise known as the delta function that sets x equals to y. So hopefully the argument that I went through there is sort of familiar to you, because I started our discussion of the Dirac equation by pointing out that every solution of the Dirac equation also is a solution of the Klein-Gordon equation. How did I show that? I started with the Dirac equation, then I acted with this complex conjugated Dirac operator, and did the exact same manipulation to show that we got a solution of the Klein-Gordon equation. And that's not an accident here. In particular, in momentum space, remember that the scalar propagator, so we could give it a tilde to remind ourselves that it's in momentum space. What was that? That was I over p squared minus m squared. Well, what's p squared minus m squared? That's the Klein-Gordon operator, right? Written in momentum space rather than position space. So the scalar operator is precisely the inverse of the scalar propagator is precisely the inverse of the Klein-Gordon operator. I mean, that's what a Green's function is. On the space of functions, you think of the Klein-Gordon operator as an operator on the space of functions. Then the propagator, or the Green's function, is the inverse of that operator. That's what it means for an equation like this to be true, because you act on it with the Dirac operator in this case, and you get a 1. Right? So if you thought about these as matrices, if you thought of the Klein-Gordon operator not as an operator on a space of function, but a matrix that acts on a vector, then the equation for a propagator is just the statement that the Klein-Gordon matrix, or the Klein-Gordon operator, times the propagator is equal to 1, which is the definition, which is how you define the inverse of an operator. So that's a very important thing to keep in mind, that a propagator is nothing more, nothing less than the inverse of the wave equation operator. And in fact, it's easy enough to convince yourself using this argument right there that as an operator, the the spinor propagator is also the inverse of the Dirac operator, right? Because how did we write it? We wrote it as I p mu gamma mu p mu plus m over p squared minus m squared. And what is that? P squared minus m squared is just using this equation right here, p mu gamma mu minus m, or let's call it plus m, times p nu gamma nu minus m. So that's I over p nu gamma nu minus m. And what's p nu gamma nu minus m? It's the Dirac operator written in momentum space. The Dirac operator is I d by dx mu gamma mu minus m. I d by dx mu is just p mu when you go to momentum space. And so this propagator is also the inverse of the Dirac operator. Sometimes we're not used to thinking of operators on spaces of functions as having inverses. But if you just think of these in your head as matrices, then it all should be reasonably clear. Indeed, if you think, as I like to do, of a quantum field theory in terms of our little lattice model of balls and springs, where phi was not an infinite number of degrees of freedom, but a set of n degrees of freedom if you have n balls on springs, then the Klein-Gordon operator is literally a matrix acting on those degrees of freedom. And the Green's function is literally the inverse of that matrix. I really think it's an instructive exercise, which I encourage you to do at some point, to actually go ahead and work that all out explicitly. There was a problem on the first problem set where you sort of did that, but it's always worth revisiting that just to make sure that you understand it, and sort of just write out what the Klein-Gordon operator looks like as a matrix. You'll have to use the definition of the derivative in order to understand what it looks like as a matrix, but it's a fun exercise to do. Actually, it's a good idea for a problem set. Try it yourselves, then you'll be ready when I give it to you on a problem set. Before I end, I just want to introduce one final bit of notation. I haven't introduced it so far, just because we were only getting to know spinors and gamma matrices and stuff like that, and I didn't want to overwhelm you with notation. But there's this lovely notation, which is usually called, I think, the Feynman slash notation. Okay. The notation is that whenever you have a vector A contracted with a gamma matrix, you just write it as the letter A with a slash through it. So the slash is a way of turning a vector, a space-time vector, into a 4x4 matrix acting on spinors. So, for example, d by dx mu, gamma mu, that combination of derivatives that appears in the Dirac equation, we write as d slash. And p mu gamma mu, the Dirac operator in momentum space is just p slash. So this is just a handy notation, and you just need to remind yourself that whenever you see a vector with a slash through it, what that means is that it's not a vector, but it's a 4x4 matrix. So D slash, for example, is a 4 by 4 matrix whose entries are various different derivatives. D by dx, D by dy, and so forth. It seems like a kind of annoying notation at first, but it does make your life a lot simpler. So, for example, you can write the propagator in momentum space as just I over p slash minus m. Or I times p slash plus m over p squared minus m squared. So these are the two free field theories that we've met so far in this class. There's one more field theory that I want to discuss before we talk about interacting field theories, and that is the electromagnetic field. So I'm going to discuss the quantization of the electromagnetic field a little bit more quickly than I did the scalar field and the spinor field, partly because it proceeds much along the same lines as the scalar and the spinor quantizations in some respects, but also partly because this quantization procedure that we have used for the free scalar field and the spinor field is actually somewhat ambiguous for the electromagnetic field. And the truly proper way to quantize the electromagnetic field involves path integrals, as we'll hopefully see later on in this class. But what I really want to do is just give you at least a schematic introduction to the quantization of the electromagnetic field along the lines of the quantization of the scalar and spinor fields, just so that you can have a full picture in your mind of the types of particles that are present when we consider these various sorts of field theories. So I'm just going to very briefly now, probably just taking up the rest of the class today, discuss the quantization of the electromagnetic field. But before I do so, let me pause and see if there are any questions. No questions? In fact, the electromagnetic field was quantized far before any of the other fields. Indeed, the whole black body disaster, which led to the origin of quantum mechanics, involves Planck's attempt to quantize the electromagnetic field in a cavity where he ran into all sorts of funny ultraviolet divergences. So, roughly speaking, the way that we proceed with the quantization of the electromagnetic field is to take the field variable, which is the 4-vector potential a mu, and we expand a mu in a family of plane wave solutions, and then promote the coefficients in this expansion in terms of plane waves to operators, and in particular to an infinite family of simple harmonic oscillators. And then the Hilbert space is just the Hilbert space of an infinite number of copies of simple harmonic oscillators, one for each possible plane wave solution of electromagnetism. So in order to work that out explicitly, we would begin by writing down the equations of motion of electromagnetism, which follows from an action. So the action of electromagnetism is something that you met early on in this course in a problem set. The equations of motion which follow from this action are just Maxwell's equations, which I will just write here very quickly. And here I am writing the action and Maxwell's equations for an electromagnetic field in the presence of some sources. That is to say, in the presence of some current that I have called J mu. But if we want to quantize the free electromagnetic field without the presence of any sources or interactions, we should just set J mu equals to 0. that would mean we're studying the plane wave solutions of Maxwell's equations. And the plane wave solutions will take the form A mu, so let me just write it as A mu of x, is equal to epsilon mu of p times e to the minus I p dot x. So again, we're studying here a solution describing a propagating plane wave with momentum p. And epsilon p here is a 4 vector which describes the polarization of the electromagnetic field. And in general, if you wanted to write out a complete basis of solutions, then you would have to consider different possible types of polarizations. So we could put a little index R here that labels the different possible polarizations of your electromagnetic field. So, of course, you all have taken classes on electromagnetism, and when you study the propagating wave solutions of electromagnetism, this is exactly what you do. You know, you might not have written it in a 4-vector notation, but you wrote out, for example, the wave solutions, the propagating wave solutions of the electric potential, say phi, or the magnetic potential, a vector, and you expanded it out in terms of polarizations, and you found that there were 2 possible polarizations for a photon. Okay? And that's something that I'll reproduce for you in just a second. But the basic idea is that one takes the field A, and just as we've already done twice today in class, you expand in a set of raising and lowering operators. So you sum over possible polarizations with coefficients A and A dagger multiplying the 2 different types. Let's call that epsilon star. So coefficients A and A dagger multiplying the positive and negative frequency plane wave solutions of Maxwell's equations. And here, just in order to keep things general, I'm going to allow my polarization vector to be complex. So for example, if you remember, if you have circularly polarized light, you usually represent that by a complex polarization vector. And so, of course, we could just keep we could keep the polarization vectors real if we liked, in which case I wouldn't have to write a star here to take the complex conjugate. But in general, it might be convenient to keep the polarization vector complex if you wanted to study circularly polarized light rather than plain polarized light. And as with the scalar field, these A's will now obey the simple harmonic oscillator algebra, so that, for example, the commutator of AP with AP prime will be equal to 0 unless P is equal to P prime. And in addition, just as with the spinor, it will be equal to 0 unless R is equal to S. So the way that you think about this is that APR dagger is the operator that creates a photon with momentum P and polarization S, or R, I guess I called it. So, for example, if you chose a basis where the 2 epsilons were left and right circularly polarized light, then you would get the raising and lowering operators that create photons. There would be 2 species of raising operator, one of which created photons that were left polarized and the other which created photons that were right polarized. And everything that we've done here will proceed exactly as it did for the real scalar field. Indeed, this is the more interesting and physically relevant case than the real scalar field, because the example that we're going to spend a lot of time studying this semester is quantum electrodynamics, and where we might be interested, for example, in calculating scattering of photons with electrons, or the anomalous magnetic moment of the electron, or something like that. And in that case, the particles that we're interested in studying are the photons that we're describing here. Now, there is an important subtlety that is different with electromagnetism than it is with the theories that we've encountered so far in this course, which is why I'm taking the time to go through this separately. But before I discuss this subtlety, let me just pause and see if there are any questions. Any questions? Yes?
What's the biggest weakness in this, what we do now? Because you said the proper way is to do it through.
Yeah. Good. So the weakness is going to be apparent in just a second when I discuss this subtlety, which is related to what's called gauge invariance. So that's exactly what I'm going to describe. But before I do that, is there any question about the overall structure here? Sometimes this quantization of the electromagnetic field is done in a quantum mechanics class, so you may have actually seen this before. So when you talk about the ultraviolet catastrophe, that's literally just studying a thermal gas of photons. Okay? You now have all the ingredients to study a thermal gas of photons. You've got a Hilbert space. What is the Hilbert space? It's the Fock space that you get by acting on a vacuum state with a bunch of these raising operators. You've got a Hamiltonian. What is the Hamiltonian? It's a sum of a bunch of harmonic oscillators with energies given by the relativistic formula for energy. In this case, the photon has mass 0, so the energy of something with momentum p will just be proportional to the square root of p squared, rather than the square root of p squared plus m squared. But it's the exact same Hamiltonian. So you've got a Hilbert space, you've got a Hamiltonian. It's a standard quantum system. You could compute the partition function, the free energy, by taking trace of e to the minus h over t. You could do all of that stuff. Sometimes that is a treatment that's done in a class on quantum mechanics. I don't know if we're going to do that here. That's not necessarily the direction that we want to go, but it's an important direction. It's the direction that Planck pursued, when he first came up with, well, the idea of quantization. There was a question in the back, though.
Yeah, so you will do RB only 1 or 2, right?
I've been a little sly about saying what it runs over for precisely that reason. But indeed, as you have anticipated, R is going to run over 1 and 2, which are the possible physical polarizations for the photon. It's not actually entirely obvious at this point that that's correct. That may be a fact, it's hopefully a fact that you remember from your electromagnetism class, but it's also a fact that we're going to derive again in just a second. Presumably, you remember from your electromagnetism class that if you have an electromagnetic wave, say, propagating in the z direction, there are 2 possible polarizations. It can be polarized in the x direction or the y direction. So there's 2 possible polarization vectors, epsilon. Okay. Or you could use a basis of circularly polarized light, so left and right circularly polarized if you wanted to. But there are going to be 2 possible polarizations. But yes, go ahead.
Yeah, because in principle it could be 4, but then we're taking masses already.
Exactly, yes. So I'm going to go through that in just a second. Yeah. So in principle at this point, as you see, as it could be any one of 4 possibilities, but there is a subtlety known as gauge invariance, which will allow us to cut that number down to 2. Any other questions? Okay, so what is the subtlety that I keep going on about? Well, the subtlety is known as gauge symmetry, which I want to spend a little bit of time discussing now, because it's a topic that will come back to haunt us again and again throughout this class. Indeed, the principle of gauge symmetry and gauge invariance is probably one of the most powerful and deep principles in theoretical physics. In the context of electromagnetism, the gauge invariance is simply the observation that the equations of motion are invariant under a symmetry which takes a mu to a mu plus the derivative of any other function lambda. And so lambda here is an arbitrary function of space, which is sometimes known as the gauge function or the gauge parameter. I don't know exactly what to call it. Let's call it a gauge parameter. So how do we see that the equations of motion are invariant? Well, remember the equations of motion, Maxwell's equations, can be formulated just in terms of the electric and magnetic fields, which are packaged into the 4x4 matrix, the 2 tensor F mu nu. And what was F mu nu? F mu nu is d mu a nu minus d nu a mu. How does that transform under a gauge transformation? Well, it picks up an extra term, which is d mu d nu lambda minus d nu d mu lambda, which, by the equality of mixed partial derivatives, is equal to 0. So the electric and magnetic fields don't change under a gauge transformation. So one very simple gauge transformation is one where you just take the electric potential and you shift it by a constant. That's one simple gauge transformation. But in fact, there are many much more complicated gauge transformations where lambda can be not just a constant, but any function of x. Just as a sanity check, one can also study how the action transforms under such a gauge transformation. Now, what was the action? It was a quarter f squared. F was invariant, plus j mu times a mu. So that's j mu d mu lambda. And that is not obviously gauge invariant until you remember that you can integrate by parts and write this as lambda times d mu j mu plus a total derivative. And d mu j mu is equal to 0 if the current is conserved. And the equations of motion of a field theory are unchanged under a symmetry if the Lagrangian changes by a total derivative. So what this means is that you can couple an electromagnetic field to any current and preserve gauge invariance only if that current is conserved. So we see here that the principle of gauge invariance is essentially the same as the principle of charge conservation. And we'll see that much more explicitly in a little bit. Not this lecture, I think, but next week. So this symmetry is all well and good, but I should point out that the symmetry is kind of different in character from the symmetries that we've met so far in this class. If you think of, for example, a complex scalar field, that has a symmetry under a charge rotation where you multiply phi by e to the I times a constant. But it was just one number. That constant was one number. Whereas here, you're shifting a not just by a number, but by a whole function's worth of things. So this is a huge symmetry, a much larger symmetry than the symmetries we've met so far in this class. There's a sense in which gauge transformations are an infinite number of symmetries. And what this means, really, is that a mu should be thought of as a redundant variable. remember that the physical electromagnetic fields are the electric and magnetic field strengths, E and B. But because of gauge invariance, for each value of these physical fields, that is to say, for each F mu nu, there is more than one possible A mu. In particular, you could always shift A mu by a gauge transformation. That would lead to the exact same F mu nu. So this gauge symmetry is a signature of the fact that A mu is really not necessarily the best variable that we should be using when we think about the basic degrees of freedom of the theory. So that leads to the following idea for dealing with this gauge symmetry, which is known as gauge fixing. So what is gauge fixing? The idea is that we should cure this redundancy of the field variable A by imposing an additional constraint on A mu such that for each F mu nu, there is a unique A mu that solves the constraints, sort of satisfying these constraints. So, for example, one simple choice of a constraint that we could impose would be to set d mu A mu equal to 0. This is a condition that is manifestly Lorentz invariant because d mu A mu is a Lorentz scalar. So if we study electromagnetism, where we impose the constraint that d mu A mu is equal to 0, then we say that we're studying electromagnetism in Lorentz gauge. So you might ask yourself whether it's always true that you can set d mu A mu equals to 0. And in fact, it's fairly easy to convince yourself that you can. Why? Well, let's imagine that d mu A mu was not equal to 0. Then you could do a gauge transformation, which would shift d mu A mu to d mu A mu plus d squared lambda. And then you could just choose d squared lambda to set d mu A mu equals to 0. Because d squared is, well, it's the massless Klein-Gordon propagator. It's invertible. So you could always just take the Green's function that we wrote down earlier and use that to solve that equation, to impose the Lorentz gauge condition. One advantage of the Lorentz gauge condition is that the equations of motion are very simple in Lorentz gauge. So let's remind ourselves, what were Maxwell's equations? Well, there they were. And this guy is just set to 0 by the Lorentz gauge condition. So Maxwell's equations without sources just say that d squared A mu is equal to 0. So it's just 4 copies of the massless Klein-Gordon equation. Now, Lorentz gauge is nice because it preserves Lorentz invariance. Very often when people discuss the quantization of electromagnetism, they use a different gauge, which is known as Coulomb gauge, sort of for historical reasons that I probably won't explain right now. But Coulomb gauge amounts to the imposition of a different set of constraints, namely that d mu, that grad A, the 3 vector, is equal to 0, and that A0 is equal to 0. Now, at first sight, it might seem surprising to you that you could just set A0 equal to 0 using a gauge transformation. But there's one easy way to see why it's the case that you can set A0 equal to 0. And that's to go back and look at the Lagrangian of electromagnetism again. So let's just look at that Lagrangian there. Look at that Lagrangian there. So what was F mu nu? It was d mu a nu minus d nu a mu. So if you think about the terms that involve A0, there's no term that involves a time derivative of A0. You know, d by dt A0, that would be d by dx0 A0, because in F mu nu, you know, F00 is equal to 0. F mu nu is antisymmetric. So there's no terms involving the time derivative of A0 in the action. What does that mean? Well, remember that when we study the canonical quantization of a theory, we introduced the momentum conjugate to a field, which was the derivative of the Lagrangian with respect to phi dot. And you see here that the canonical momentum conjugate to A0 is equal to 0, because A0 dot does not appear in the action. So that means there's no momentum conjugate to A0. So it's not really, you shouldn't really think of it as a dynamical variable. It's not something that fluctuates. It's like if you had a theory for, it's like having a Lagrangian for a particle without a kinetic term. And so because of that, you can actually study electromagnetism in a formulation where A0 is just set equal to 0. And actually, I think it's a fun exercise that you should go through and convince yourself that you can always find a gauge where these 2 Coulomb gauge conditions are satisfied. If it's not obvious to you, first just imagine, how does a vector shift under a gauge transformation? Well, it goes to A plus grad lambda, so that del dot A goes to del dot A plus grad squared lambda. So if del dot A is not equal to 0, just choose lambda such that grad squared lambda cancels del dot A. That's how you impose that first condition right here. And then to impose the second condition, investigate how A0 transforms. And then you can hopefully convince yourself that you can still do a gauge transformation that preserves this condition while simultaneously setting A0 equal to 0. That's a nice exercise. Maybe if you find it non-trivial or a little challenging, let me know and I'll put it on a problem set. So the reason why I think this gauge is useful, because in this gauge, what are the polarization vectors? Well, first of all, what is the equations of motion? The equation of motion just says that d mu, a vector is equal to 0. Why is that? Well, you could go up again and look at the equations of motion that we wrote down up here. So there was your d mu, a vector. And then you can easily you can just see that with the Coulomb gauge condition, this term is not going to matter. So again, you have d mu, a mu is equal to 0. And the polarization vectors, what is it? Well, it has to obey these 2 gauge conditions. which means in momentum space, so epsilon 0 is equal to 0, and k dot epsilon is equal to 0. That's just the usual statement that you're probably familiar with from electromagnetism, that the polarization of an electromagnetic wave is transverse to the direction of propagation of the wave. It turns out that's a consequence of what gauge we chose. You could choose other gauges where you have, I suppose, a longitudinal polarization of the photon in its direction of propagation. So, for example, the epsilon mu's that I wrote down above, you could write them as epsilon mu 1 and epsilon mu 2, so that label R that labeled the different polarizations would run from 1 up to 2, where you could then just choose a set of epsilon mu's that obey these two equations. So, for example, for a photon propagating in the z direction, you could take epsilon 1 and 2 to be 1 plus or minus I in the x and the y components, and 0 in the t and the z components. These would describe left and right circularly polarized light, respectively. Or, if you wanted to work in terms of linearly polarized photons, you would take epsilon 1 to be 0, 1, 0, 0, and epsilon 2 to be 0, 0, 1, 0. It's just a choice which polarizations you choose. But in general, the point is that we have two choices of polarizations which obey P contracted with epsilon is equal to 0. And that actually turns out to be a general condition no matter what gauge you're in. So this was a rather quick introduction to the quantization of electromagnetism. I didn't go through it in too much detail because it really is very similar to the quantization of the scalar field and the spin 1/2 field. So I don't want to spend too much time on it before we can get to the good stuff. Of course, there are many computations that one could do. One could compute the Hamiltonian, write it out in terms of raising and lowering operators. I was going to give that to you on the problem set, but then I decided that was too annoying. We could also compute the propagator. So the propagator is now a 4x4 matrix. So I'll give it two indices, mu and nu. And the important thing to remember about the propagator is that it is actually ambiguous because of gauge invariance. In particular, under a gauge transformation, A mu shifts by a total derivative. So this propagator will shift under a gauge transformation. So you just choose a gauge, you choose a condition to impose, and work with the propagator in that gauge. And if your theory is gauge invariant, if charge is conserved, the answer that you get will be independent of your choice of gauge fixing. So you just choose whichever one makes your life most convenient. And in fact, it's easy to guess what the propagator is in the gauge that we have chosen. So I'm actually going to cheat a little bit because I'm running out of time. and just write down the answer for you. But you can easily guess the answer. It just follows from the fact that the equation of motion is just the massless Klein-Gordon equation. So you would think that the propagator is just the propagator of the massless Klein-Gordon equation. Except it's the massless Klein-Gordon equation for 4 fields. So in fact, you can write it as I times g mu nu over q squared plus I epsilon. Oh, sorry, p squared plus I epsilon. I'm actually cheating a little bit when I write this expression. I mean, this is what you would guess because it's a massless Klein-Gordon propagator, and each of the fields independently obeys it, and they don't mix with each other under the equations of motion. But it's actually a little bit of a cheat. Okay? So unfortunately, I was hoping to finish this today so that we could move on to interactions next time. But I think rather than trying to rush through it and keep you here afterwards, I'll just finish this next class. But maybe before I stop, I should pause and see if there are any questions. Or actually, maybe what I'll do is maybe we should take this as a given and just say in a certain gauge that's known as Feynman gauge. And then when we revisit the quantization of electromagnetism using path integrals, we'll actually do the proper calculation. In particular, the only calculation that I wanted to do is I just wanted to check that this is the inverse of the equations of motion, just as the Klein-Gordon propagator was the inverse operator for, or the propagator of a scalar field is the inverse of the Klein-Gordon operator. The propagator for the spinor is the inverse of the Dirac operator. And this propagator that I've written here is the inverse of the Maxwell equations. In particular, if you just look at Maxwell's equations here, and you choose, say, Lorentz gauge where this guy is equal to 0, then hopefully it's clear that, you know, in momentum space, you just get p squared times a nu, so that the propagator is just going to be 1 over p squared. So maybe we'll just take that, leave that as an exercise, so that I can begin next week fresh with the discussion of interactions in quantum field theory. Any questions before I end? Sorry for going over by a minute or two. Yes?
And when we introduced the axiom, it was to separate the poles in the complex plane.
Yes.
But now, I mean, it's like we have a single pole. There is no,
It's a double pole still.
okay.
Right. They're very close to one another, right? So it's a little, yeah, that's right. You still have two, it's like the poles have coalesced. But they now will get separated by this I epsilon. That's actually an important point. So that when we do the time ordering prescription, one of them, you know. It's- No, yeah, that's right. So now it's a second order pole. It's no longer a simple pole on the complex plane. That's actually a very good point. Yeah. I mean, I'll be completely honest, which is that, strictly speaking, there is no derivation of this in canonical quantization that's completely correct. So the procedure that we've been using so far in this class, where we take a field, we expand it in terms of raising and lowering operators, and then start computing from there, is known as canonical quantization, because p's and x's are canonical variables. It turns out there's actually no completely correct derivation of this using canonical quantization. The proper treatment of it uses path integrals. So for now, we can just take this as given, and we'll return to this when we discuss the path integral quantization. Good. Yeah. Great. Any other questions? Okay. See you next week.